Hello there, and welcome to Forces 2, Part 1. This is going to be on Lesson 5, which is on Newton's first and second law of motion. If you want to really quickly take a look at the first page on page 43 of your Forces 2, Part 1 booklet, you'll notice that there is a chart, and I haven't mentioned this before, but you should be really using this chart to kind of summarize what you need to be able to get out of this lesson, because this chart is actually taken straight out of the Department of Education in terms of what can be tested on your GCSEs. All right. That being said, can you please start with the do now? 8 questions, really simple, has to do with the previous content that you learned in the previous lessons. All right. So pause the video, go ahead and do that. All right. So I'm going to show you the answers. And like I said before, this is all content that you have learned before. Nothing too confusing there. Just want to make sure that you do understand some of the units, the equations, as well as how to utilize some of the graphs, such as a velocity time graph or a distance time graph. Okay, so we're going to start off with kind of overviewing what we're going to learn today, and that is Newton's first and second law of motion. Okay, and you need to know the actual law itself, as well as Newton's second law actually has a equation attached to it, but it's actually one of the most easiest equations to memorize in physics, so you don't need to worry about that. So the first thing that we want to make sure that we have a very, very good grasp on is resultant force. All right, so this is a term that you have heard before in previous lessons. And if an object has a resultant force, then an object's state of motion will change. Okay. Now, if you don't remember, resultant force is basically if you combine all the forces that are acting on one object and it comes out to one definitive force or one definitive arrow. Okay, so this means that if something was stationary, it's going to start moving, and if it's moving, it's going to either speed up, slow down, or change direction depending on the direction of the resultant force. Okay, so what we want to look at is this diagram here. Okay, so this car is moving towards the left because, as you can tell, the front of the car is towards the left. And we can see that there are 4 forces acting on this car, but one of the forces is actually a lot longer than the other 3, and that is the left force there, the force going towards the left. Okay, so there's actually a resultant force in this car, and it's going towards the left. And something that you're going to learn to recognize is that if you have a resultant force, this is going to cause an acceleration in the object. Okay, so if I were to draw the actual resultant force of this car, right, I wouldn't really draw all 4 arrows because this is what's called a free body diagram. The resultant force diagram would look something like this. Okay, so like I said before, it's a combination of all the different forces that are on there, which means that if you have 2 forces that are going in opposite directions and they're equal, such as the top and the bottom force, they're going to equal out. And then for the left and right forces, because they're unequal, right, it's going to go towards the direction that has the bigger force. So the last sentence on this section here says, label each of the forces on the diagram. So we're going to start with the left and the right one first, because this one should be the most straightforward one. So you have your thrust and your drag. And drag can be also replaced with air resistance if you wanted to use air resistance. Drag is just a shorter word, so I thought that would be easier for you guys. And the top and bottom one, now this is something that you may not have seen before, because most of the free body diagrams that you guys work with is usually like free falling diagrams, like a ball is falling or a skydiver is falling. So you haven't really looked at anything that was kind of on the ground. And you might think, oh, if something is on the ground, there's no forces acting on it because it's not moving anywhere. Well, even if it's not moving, there are still forces acting on that object because we all feel the force of gravity, right? Gravity is what keeps us on the ground, and that's actually a force, okay? So you guys already know that if there was no gravity, then we'd just start floating. So there actually has to be a force that pulls us down to the ground. And because we're not constantly falling, there has to be an opposite force that goes the opposite direction. Okay, and we're going to call that support force. Okay, and that just basically means the force that is acting on the car in this case from the ground. So if the car is exerting a force on the ground, then the ground has to exert an equal force back. Okay. So before I move on, I just want to clear up a common misconception that most students have. And the example that I'm going to use is what I usually use to explain resultant forces, and that is a tug of war. Right? So most of you have heard of this, or you may have played it before in primary, but in a tug of war, basically whoever has the stronger side or whoever pulls the strongest is going to win, right? So in this scenario, there are two forces, right? And each force is applied by each team. So in this case, in this diagram, we have two teams, and they both apply a force in opposite directions. Now, obviously, like I said before, whatever force is bigger has to have, or is going to win, correct? So the misconception here is, if I asked you guys to draw the resultant force of this diagram, all right, it would be 0. Like, you wouldn't draw anything because both forces are equal to each other. So the resultant force is 0, right? But most students will say, okay, now I changed the diagram. Now the force going to the right is a lot bigger. Okay, so what does this actually mean? And most students will say, oh, the resultant force is going to the right. And say, yes, you're correct. Now, what speed is it traveling at, right? How fast is the other team pulling on the rope? And you might think, oh, well, depending on the numbers, they're pulling it at like, I don't know, 3 meters per second. Okay, and this is where most students will find this problem, because it's not velocity. If you have a resultant force on an object, that actually means that that object is accelerating. Okay, and from last lesson, you guys learned that acceleration is the rate of change in velocity. So if something is accelerating, it's getting faster. And you might think, well, it's not actually getting faster, it's just moving, isn't it? And if it's just moving, then that means there's no resultant force. It's moving, and that's it. So this is the problem with Newton's first law, is most students will come into it thinking if it has a force, it has to be moving. But what they don't understand is it's not only moving, it's moving at an acceleration. Okay, so just be wary of that, okay? And we'll move on to the checkpoint questions. So the first checkpoint question on page 45 asks, what can be said about the braking forces and driving forces when a car is traveling at constant velocity? So this is the point that I was trying to get at, okay? So the braking forces and the driving forces are just generally two forces that are working in opposite directions, right? Driving force means they're going forward. Braking force means it's trying to repel that driving force, right? Or trying to stop that driving force. So if a car is traveling at constant velocity, is there going to be a resultant force? Okay, and the answer to this is, well, not really, right? Because both forces are equal, okay? And so Newton's first law basically says something along the lines of an object will stay at rest or at constant velocity if there's no resultant force acting on it. Okay, so in physics, this is where most students get confused, because you think, oh, okay, a car is moving at constant velocity. There has to be a force driving it forward, right? And yes, there is a force driving it forward, but there's also a force pulling it back, which in most cases is air resistance, that keeps it traveling at constant velocity. And so the resultant force of that object is eventually going to be 0. Okay. As I explain this more and more, hopefully you kind of get it to understand, but if not, there's always supplemental videos that we can share with you if you don't understand this. The second checkpoint question asks, if an object changes direction but remains at constant speed, is there a resultant force? So the key word here is it remains at constant speed. Okay, and so the answer here is no. Okay, and let me just illustrate this really quickly. If you have a car that's going to the right, all right, at constant velocity, there's no resultant force. Both forces are equal to each other, right? Let's say that car changes direction. Now it goes to the left, but it remains at constant speed. The answer would look something like that. Okay, so it goes the opposite direction, but forces are still equal to each other, so there's no resultant force. Right, so let's actually get to Newton's first law, and I'm going to try and make this as simple as possible because physics is hard to visualize, okay? So you have to kind of visualize with me here. So Newton's first law says, if the resultant force acting on an object is 0, and there's two scenarios that you have to look at. So the first scenario is the object is stationary, then the object will remain stationary. So now remember that stationary means that it's at rest, okay? So basically, I'm going to just flip this around. If an object is at rest, okay, and the resultant force acting on that object is 0, then it's going to stay at rest. Now that seems like it makes sense, right? So the diagram on the right there with the car with the arrows going up and down shows an object that is at rest, and it will stay at rest, okay, because the resultant force acting on it is 0. So both forces, which is up and down, are equal. So the resultant force along the y-axis, which means that you go up and down, is 0. Okay. Now imagine if those forces were unequal, okay, then the object will start moving in the direction that's stronger, okay? Now, the second scenario is where you might get confused, okay? So an object is moving. So the object continues to move at the same speed and in the same direction. So the object continues to move at the same velocity. So this one, I'm not sure how more simple I can put into it, but basically if an object is moving at constant velocity, it will continue to travel at constant velocity unless there is a change in resultant force. That's pretty much how simple I can put it, and I'll try and explain it more and more. So in this diagram here on the left, all forces along their respective axis are equal, so the total resultant force is 0 on that car, correct? Okay, that should make sense, because if you're just looking at it, you're thinking, right, they're all the same forces, so I mean this car it's not moving. And that's what you might initially think, but then you look at it closer and think, wait, but there's a forward force, right? There's a force driving it forward and the force driving it back, right? And generally this just means that the car was moving, right? But since the forward and backwards forces are equal to each other, it's just there's no change in velocity, right? And change in velocity is acceleration. So hopefully you kind of make that distinction between the steps, all right? But when we do some practice problems, you'll kind of understand what format the questions will come in when you understand this. Because in physics, they have to tell you, for questions like these, they have to tell you what situation the car was in before you take into account all the resultant forces. So if you didn't know that the car wasn't in motion, then you can't really say for sure if it was at rest or if it was in motion when the resultant force is 0. Okay? But you have to recognize that the left diagram has arrows going forward and backwards, so you have to assume, okay, if there's a driving force, then the car was moving. Okay? The one on the right is at rest because there's no forward and backwards motion, so it's just kind of standing, or it's just sitting there. Okay? So I'm just going to read out the last sentence here. So when a vehicle travels at a steady speed, the resistive forces balance the driving forces. So the velocity, speed, and or direction of an object will only change if the resultant force is acting on an object. Okay? I'm going to just add on one more diagram here. Now you don't have to draw this if you don't have to, but I think it kind of helps understand a little bit more about how this works, because you've been looking at cars and the top and bottom forces are really what kind of confuse lots of students. So I'm going to divide this up into horizontal and vertical forces. So the thing I want you to understand here is that your horizontal forces will not affect the vertical movements. So in this case, for the submarine, the engine, it's what's driving it forward, right? So the engine driving it forward will never impact how it sinks or how it rises. That's a completely different function in submarines. And likewise, the component of a submarine that controls whether it rises or falls in the ocean will not affect whether it goes left or right or front or back. Okay? So in this case, your horizontal forces are balanced. So the horizontal resultant force is 0. So I'm working through a step by step. Normally you would do all 4 forces at once, but I'm working with the horizontal ones first and then the vertical ones. Now, if you look at water resistance and engine force, they're generally about the same, which means that the resultant force is 0, which means that there's no acceleration. Okay? Now looking at the top and bottom one, buoyancy and weight, the vertical forces are again equal in size, but opposite. So that means that they're balanced as well. And so the vertical resultant force is also 0. Now, when you combine the vertical resultant force and the horizontal resultant force, that's when you understand, okay, it's not 0. Okay, or sorry, sorry, I'm not trying to confuse it. It is 0, all right? Where it gets into a little bit more confusing stuff is, let's say they're unequal, both of them, and then you get into, diagonal forces, okay? But obviously you don't need to know that right now. But in this scenario here, all right, you might want to ask yourself, is the submarine moving at constant velocity or is it at rest? Okay, I'll give you 2 seconds to figure that out. Is it moving or is it at rest? And if you said that it's at rest, you are wrong. Okay, this like the diagram on the previous page, right? If the car had four forces, and that represented that the car was moving, but it was moving at constant velocity. So same with the submarine. There's four forces, which means that the submarine was moving, but since all forces are equal to each other, that means that it's moving at constant velocity. There's no acceleration here. Okay, but if water resistance was less than engine force, then this submarine would be accelerating forwards. Or if buoyancy force was bigger than weight, then the submarine would be rising. All right. Okay, so let's just answer really quickly on page 46 the checkpoint questions, and that is basically what are the first two laws of Newton's law of motion. Oh, sorry, no, this is just the first laws of both ones. So if you want to go ahead and pause the video and answer those really quickly, you can do that. Otherwise, I'm going to move along. State Newton's first law for a stationary object. So if an object is at rest or stationary, and the resultant force is 0, then the object will remain stationary. All right. So easiest way to explain this in simple terms is an object will remain at rest, an object that is at rest will remain at rest unless there's a force acting upon it. And Newton's first law for a moving object is if an object is traveling at constant velocity or constant speed and the resultant force is still 0, then the object will remain moving at constant speed. So this one, again, in simple terms, is an object will move at constant velocity and will remain at constant velocity unless there is a force acting upon it. Okay, and in this case, the force I'm talking about is the resultant force. Okay, so let's do some practice problems. And what I'm going to get you guys to do is go ahead and pause the video. There's 4 questions. They're all kind of linked towards each other. It's more 2, 3, and 4 linked together, and then 1 is by itself. But again, if you guys don't even know the question or don't know the answer, read the questions carefully, because I think I mentioned to you guys before, there are lots of questions like these on your GCSEs that are more or less hidden multiple choice questions, right? They're just lengthy in word. So you want to read it carefully and recognize, actually, this is a multiple choice question. Okay, so go ahead, pause the video, and do that. Okay, number 1. The diagrams A, B, and C show the horizontal forces acting on a moving car, and you want to draw a line to link each diagram to a description of the car's motion at the moment when the forces act. Draw only 3 lines. Now, if you can notice, this is a multiple choice question, and for each one you have 4 choices. Is it stationary, constant speed, slowing down, or accelerating forwards? Right? So even if you didn't know the answer, you have a 25% chance of getting this right. So let's go down the questions here. A, you have 500 newtons going forward and backwards. So is this at rest? Is it constant speed, slowing down, or accelerating? Now, the first thing you should do is recognize that the first 2 options, stationary and constant speed, are only for those that have a resultant force of 0. And then if it's slowing down or accelerating forwards, those are the ones where the resultant force is not 0. So for A, you only have 2 options really. Is it stationary or is it constant speed? Now, like I mentioned before, if you have forward and backwards motions on it, then that car is actually moving. But since the resultant force is 0, you have constant speed. For the next 2, this one should be pretty straightforward. If you have 500 newtons going forward and 200 newtons going back, what's the resultant force? 300 newtons going forward, which means that it is accelerating forwards, and that only leaves the last one to be slowing down. Okay, so hopefully that makes sense to you, because like I said, the ones where the resultant force is 0 is going to be the confusing ones, where you kind of have to think about, was it originally at rest or was it actually moving when I'm looking at this? All right, number 2. The front crumple zone of a car is tested at a road traffic laboratory, and this is done by using a remote control device to drive the car into a strong barrier. Electronic sensors are attached to a dummy inside the car. So a lot of information in there that you don't really need to know, because if you look at the questions that they're asking of you, it says draw an arrow in box 1 to show the direction of the force that the car exerts on the barrier, and number 3 asks draw an arrow in box 2 to show the direction of the force that the barrier exerts in the car. So for this one, again, it is kind of a multiple choice, but it's more of a true-false 50-50 type of answer. because there's only two ways that the arrows can go. It's either left or right. So for box 1, it's asking what direction of the force that the car exerts on the barrier. All right. So the key things to recognize here is, what are you looking at? Are you looking at the car or are you looking at the barrier? And in this case, you're looking at the car, right? So the car, which direction is it moving? It's going towards the barrier, which means that the force of the direction is towards the barrier. Okay. So then number 3, if you got number 2 right, then hopefully number 3 came kind of as process of elimination, because there's only one other way that the barrier can act, and that is the opposite way. Okay, so that's number 3 right there. And really, if you understood the concept that for every force there's an equal and opposite force, box number 2 kind of comes secondhand to you, or naturally I should say, because if a car exerts a certain amount of force on the barrier, then the barrier has to exert an equal and opposite force towards the car. Number 4, complete the following by drawing a ring around the correct line in the box. The car exerts a force of 5,000 newtons on the barrier, and the barrier does not move. The force exerted by the barrier on the car will be more than, equal to, or less than 5,000 newtons. So again, this is kind of carrying on from question 3. And the key thing to notice here is that they specified that the barrier does not move. All right, which means that the barrier is strong enough to withhold all of or just about 5,000 newtons. So that should cancel out less than 5,000 newtons, and it's a choice between equal or more than. But even if you didn't know any of this, guess, right? You have a 33.33 repeating chance of getting this right. But since it didn't move, then you want to say that the barrier on the car will be equal to 5,000 newtons. Okay. All right. This brings us to Newton's second law. All right. Now I told you guys that there is a equation related to this, but I told you guys it's one of the easiest equations to memorize in physics, so don't you worry. So Newton's first law deals with situations where there's no resultant force. Okay. And so we're looking at objects that are stationary or moving at constant velocity. Newton's second law, on the other hand, deals with the situation when there is a resultant force. And so if there's a resultant force, that means that there's acceleration, and from there we can actually calculate a lot of different things. So the acceleration of an object is proportional to the resultant force acting on an object and inversely proportional to the mass of the object. Now that is a lot of confusing mumbo jumbo there, but what they've actually done is they've actually just put the formula that you're going to learn into words, okay? And all they're saying is the relationships between force, mass, and acceleration. And so this is the equation that you have to memorize, is force equals mass times acceleration. And this is probably one of the most commonly used formulas in physics that has to do with motion. Because if you look at it, it's one of the most simplest. You got force, which is always in newtons. You got mass in kilograms, and then acceleration in meters per second squared, right? And so let me just kind of clear this up for you, okay? The second law states that the acceleration of an object is dependent on two variables, and that is the net force acting on an object and the mass of an object. And hopefully this comes like, oh yeah, that makes sense. But if it doesn't, let me show you a diagram that does, okay? So let's say you have two objects, right? And you throw each one, but you throw each one with different forces. You throw one with like 100 newtons and you throw another one with like 10,000 newtons, right? Which one's going to travel, or which one's going to accelerate much faster at the point when you throw it? The one with 10,000 newtons, right? And that's just because you have a lot more force behind it. And you're thinking, oh yeah, well duh, okay? And so, but this, we didn't really put it into a mathematical term at the point when this was discovered. So we just kind of assumed, yes, that makes sense. The other thing that affects something's acceleration is how heavy it is, right? So if you're pushing something with the same amount of force, but you have two objects, you have a car and, I don't know, you have a cardboard box, right? And you push both of them with the same amount of force. Which one is going to accelerate faster? Obviously the cardboard box, right? And I'm just saying that because I have a cardboard box in front of me. But you get the point, right? Whatever's heavier is going to require a lot more force to make it accelerate at the same pace as that cardboard box, okay? So this equation that Newton came up with was just mind-blowing. Like, how did he figure out a mathematical way to express that the acceleration is dependent on the mass and the force, right? So hopefully from this, you should be able to rearrange the formula. I haven't written it down, but F equals m times a, or you can get m equals F divided by a, or a equals F divided by m. So you need to be able to rearrange the formula. You can make the triangle if you wish, but I didn't put that up there as always because I don't want you to rely on that triangle. Just try and memorize this formula and then how to rearrange it. So, checkpoint questions. State the defining equation for Newton's second law and state Newton's second law in words. All right, so go ahead, pause the video and do that really quickly. And state the defining equation for Newton's second law. This one's quite easy. F equals m times a. When I was in high school, in school, and I learned this equation, my friends and I, we would just joke about this, and we would just go around saying "fama, fama," and that would kind of help us memorize this equation for some reason, and it stuck. So whatever works for you guys. And then state Newton's second law in state Newton's second law in words, and this one's pretty straightforward. Newton's second law says that the accelerations depend on the force and the mass, kind of what I said before. If this works out better for you, or if you understand this better than what I highlighted in yellow on the previous slide, then go ahead and use that. They're both essentially the same thing. It's just the other one uses a lot more complex terms like inversely proportional or directly proportional. Although you do need to know those terms. I'm not kind of downplaying that there. This is a lot more easier to understand. All right, so let's actually use this equation for this exam style question, okay? So you have a cannon shell that's 2 kilograms in mass and accelerates at 30 meters per second squared. So how much force through that cannon shell, right? So let's work this out. First, you want to start off with the equation F equals m times a. Now, you don't need to rearrange anything because you're just looking for force. All right, so force is what your equation wants to start out with because that's what you're looking for. And like always, like I mentioned, guys, you most likely will get a point for just substituting the numbers into the actual equation because that step basically shows the examiner that you know which you know which formula that you want to use, okay? And you know which letters represent what. So m represents mass, which was 2, and the acceleration, or a, was 30, so 2 kilograms times 30 meters per second squared, and that should give you a force of 60 newtons. Okay, so just the key thing to remember here is, again, you choose the right formula and get the right units. Okay, I'll do another one with you, and then you can do the rest by yourself. So jet ski weighs a lot, 120 kilograms, and it only accelerates with 3 meters per second squared. So same thing, you want to use F equals m times a, and then substitute the numbers. Mass for this one was 120, acceleration was 3, and you multiply those two together. 3 times 120 is 360. Okay, so that's your second answer right there. So hopefully this kind of puts into perspective, like, you know, you have a lot of force, right? But your object is, you know, a lot heavier than just a cannon shell. Okay, so using this process, go ahead and figure out the other 4. It should be pretty straightforward here, and I'll let you pause the video and go ahead and do that. Okay, so football weighs 0.2 kilograms, accelerates at 8 meters per second squared, multiply them together, and you get 1.6 newtons, and you get 4 newtons of force if you shoot an arrow at the acceleration of 40 meters per second squared. A yacht travels at 1.5 meters per second squared, accelerates, and so the force probably generated from the engine of the yacht is 30,000 newtons, and then a train weighs a lot more, accelerating at 2 meters per second squared, has a resultant force of 600,000 newtons. Okay, right. So Newton's second law is just that. It's just the equation, and then understanding that there is some form of relationship between mass, force, and acceleration. The rest of this lesson is all practice, and so what I'm going to do, and it's totally up to you guys because I'll give you a bit of time before each question, is I'm going to basically ask you guys to pause the video and go ahead and work on the questions that you know between numbers 1, or sorry, this is number 2. Sorry, numbers 2 to 11. Okay, work on the ones that you know and you are confident that you can solve, and then I will run through all of them together without pausing for the rest of this video. Okay, so go ahead and do that, and I'll see you in a little bit here. Okay, so let's get started. All right, number 2, figure 1 shows a distance time graph, key thing, distance time, for a person walking to a bus stop. Which one of the following statements describes the motion of the person between points R and S on the graph? So if you look at R and S, this person walking to a bus stop traveled 0 meters in 50 seconds. Right? So 0 meters in 50 seconds, that looks like someone is not moving at all. So you just want to tick the correct box, which is they're not moving. Okay? So that's number 2. Really easy, straightforward, 33.33% chance. If you don't know the answer, just guess. All right? And I'm saying guess now, guys, because on your GCSEs, you don't get any deductions of points if you're guessing. All right? So if you want to try and get as many points as you possibly can, guess on as many questions as you possibly can on the ones that you have absolutely no idea on. If you have some inkling of what you're doing, then make an estimated guess at least. Okay. All right, number 3, another person, so this is the same scenario, another person walking at constant speed travels the same distance to the bus stop in 200 seconds. All right, so complete figure 2. So all you have to do is draw some line or something on the distance time graph for this person. So let's compare the two, right? The first person, now it doesn't actually tell you how far this bus stop is, but you are able to figure it out from the first diagram in figure 1. And in figure 1, this person got to the bus stop in 300 seconds, okay? But you might be asking yourself, well, okay, I know that it was 300 seconds, but how far did they travel? And if you look at the very top of that line in figure 1, they reached 500 meters. Okay, so you know that this bus stop is 500 meters away from the starting point. So that should tell you how far up you should go on your y-axis. And then as far as your x-axis, this question says travels the same distance. Okay, so 500 meters in 200 seconds. So you want to go from 0 to 500 meters in 200 seconds. So this is what your graph should look like. Okay, so notice how I start off at 0, 0, and then I end at 200 seconds and 500 meters. And I just connect the two dots together. Okay, simple as that. And this person, they don't say anything about this person stopping or slowing down or speeding up. So you have no need to do anything of that. Very simple question. And before I move on, I'll just say that this comes from understanding graphs and all that stuff. So, when I tell you guys to look at the graphs carefully, I really mean it, because some students will just think, oh, maybe it's a velocity time graph, or maybe I don't know what this graph is telling me, right? Well, look at the graphs, all right, and understand them as best as you can, please. All right, number 4, a bus accelerates away from a bus stop at 2.5 meters per second. The total mass of the bus and the passengers is 14,000 kilograms. Calculate the resultant force needed to accelerate the bus and the passengers. So there's a couple things given to you. Those two things is the acceleration and the mass, right? So whether you wrote it down like this or you highlighted it, don't really care, as long as you can understand that's what you're working with. So now you want to say, okay, what formula do I need to figure out from here? And that is calculate the resultant force. Okay, so you want to use an equation that says F equals, what's the rest of that equation? And the answer is FMA. No, I'm just kidding. It's F equals M times A, right? So all you have to do is replace the numbers. So F equals 14,000, which is the mass, right? Mass is 14,000 times acceleration, which is 2.5, and you get a total of 35,000 newtons. Okay, simple as that. 2 points, 1 point for the answer, 1 point for the substitution. Okay, just remember that you don't get any points for writing down things like A equals 2.5 and M equals 14,000, because that doesn't really show you really much, right? It just means that you're able to copy down numbers and that's it. Okay. Number 5. So this one's a new type of question. A trolley is attached to two identical springs. The trolley is pushed to the left and then released. Figure 1 shows the horizontal forces acting on the trolley just after it is released. Write the equation which links acceleration, mass, and resultant force. So this one should be quite easy. That one is just F equals m times a. And number 6 asks, if the trolley has a mass of 0.75 kilograms, calculate the acceleration of the trolley just after it is released. Now, this is all falling back to Newton's first and second law of motion. So first of all, if you look at the trolley, you have two forces acting on it. You have 1.5 newtons going to the left and 2.7 newtons going to the right. So is the resultant force 0? No. You have two forces in opposite directions, right? And they're not equal. So that means that whatever force is bigger is the direction that you're going to go in, right? So in this case, you already know because it described it to you, right? The trolley is pushed to the left and then they released it. And if it has two springs, it's going to, jump back and forth, right? So let's write out the equations here, right? So F equals m times a. Now, is this the equation that we want to work with? And the answer to that is no, right? Because we want to look for acceleration. So we want our equation to start off with a equals. Acceleration equals, and that should equal a equals F divided by m. Now, the next portion here is why this is worth 4 points. All right, it's a pretty tricky one, and it's meant to trip up some students. And I put the force is 1.2 newtons. All right, because if you look back at the formula, F isn't just any force. Okay, so I know some of you might have put 2.7 newtons, right? Or you might have put 1.5. Who knows? But 1.2 I got from subtracting 2.7 and 1.5. And why did I do that? Because resultant force is the force that you're looking for in F equals m times a. All right? And resultant force is a combination of all forces. So in this case, you have two forces going back and forth. And in order to get the resultant force, you just have to subtract them. That's what we did, I think, in Forces Part 1, where if you have two different forces going opposite directions, you just subtract them to find the resultant force, right? So that's how I got 1.5. The mass, it's given to you, 0.75. And 1.2 divided by 0.75 gives you 1.6 meters per second squared. Now this one, they don't give you the units, so I'm going to say that that's where you get the other point for the total of 4 points. Okay, so if you want it broken down, 1 point for the answer, 1 point for the units, 1 point for substitution, and 1 point for figuring out that force is going to be 1.2. Okay. Number 7. So the diagram shows a boat pulling on the water skier, and the arrow represents, so if you see the arrows coming out from that propeller at the back of the boat, the arrow represents the force on the water produced by the engine propeller. So this force causes the boat to move. Now this one is the same type of question before where we were asking, what exerts or which direction does the car exert on the barrier or the barrier and the car, right? So this one specifies that the arrow shows you the force produced by the engine. So they kind of switched it around, right? So really, if you wanted it in the exact same words as the previous question, it would have said the arrow represents the force the engine exerts on the water. That's really what it should say, but that's what I'm going to write. The arrow represents the force on the water. So the engine also produces a force moving in the opposite direction that is much bigger, and this will cause the boat to move forward. You could also say that the water resistance, I guess, or drag is a lot less than the forward motion, which causes it to move forward. But either way, however you want to explain it. Number 8. The boat accelerates at a constant rate in a straight line. This causes the velocity of the water skier to increase from 4 meters per second to 16 meters per second in 8 seconds. Calculate the acceleration of the water skier and give the units. So you're looking for acceleration, but something is wrong because you don't have force and you don't have mass. what's given to you is velocity and time. So you're not actually using the formula that you learned in this lesson. You have to bring back some of the original equation that you learned previous, which is A equals delta V divided by T. And delta V, as you remember, is change in. So if you're going from 4 to 16 meters per second, then your change in velocity is going to be 12 meters per second, and you did that in 8 seconds. So you have 12 divided by 8, and that gives you an acceleration of 1.5 meters per second squared. And don't forget that you have to put 16 at the front because it's final velocity subtracted by initial velocity. So you went from 4, which is your initial, to 16, which is your final. And it looks like I've already put number 9 on there since the beginning. I totally didn't recognize that. But now you're given a chance to figure out what you used, or sorry, what is the actual force acting on the water skier while accelerating. So you have your acceleration now, which is 1.5, and you have a mass, which is 68 kilograms. So all you have to do is force equals m times a, which is 68, mass times acceleration 1.5, and that gives you a force of 102 newtons. For this one, if you were marking number 9 and you did the process correctly, so if you got an answer and you did the procedure right, so you multiplied your mass times whatever you got for number 8, then you can get up to 1 point. So obviously you get full marks for getting 102, but you can get 1 point for substituting the correct numbers in. So even if you got number 8 wrong, you can still get points for number 9, if that makes sense. Okay, number 10. So this is one of the questions where you might have to think a little bit, but there's actually 2 ways that you can answer this. All right, so I mean, that's good for you guys because the more chances that you have at getting a question right, the better your chances. What you want to do is you want to calculate the deceleration of an oil tanker. Show clearly how you work out your answer. All right, so you're given mass, cruising speed, deceleration force, and stopping distance. So basically you're given M, V, F, and S. If you remember what S is, that's basically your distance or displacement. So I'm going to show you the first way to do this. And this one is probably the simpler one because there's less variables. But calculate the deceleration of an oil tanker. So you want to use A as your subject. So A equals F divided by M. And in this case, your F is given to you as 392,000 newtons divided by the mass, which is 56 million kilograms. These are pretty big numbers, so when you put them in your calculator, do not mess this up. And when you do all that, you actually get a value of A equals 0.007 meters per second squared. So really, really slow deceleration. And I actually messed up something here because if you guys are looking at this thinking, no, you're wrong, you are right because I am missing something, and that something is a negative symbol. So deceleration is another way of saying negative acceleration. So it should say minus 0.007 meters per second squared. So that's one way to do it, which is, like I said, the easier way. But if you want to do a little bit more work, then you want to use a different formula. And that formula, same thing, still has to start with A equals, but this one looks like this. V squared minus U squared divided by 2S. Sorry, that should say S, not A. And this one comes from the equation V squared minus U squared equals 2A squared. And that is one of the equations that's actually given to you on the physics equation sheet. So you don't have to memorize this, but rearranging that formula comes a little bit more complicated. So, sorry, it should be 2AS equals V squared minus U squared. That's the equation that's given to you on the physics equation sheet. So if you want to figure this out, basically you have A equals 0 squared minus 12 squared divided by 2 times 10,000. And you're thinking, where did I get 0 from? And that's because you're assuming, and this is why this is the more complicated way, you're assuming that the cruiser will come to a stop if it's decelerating. And so 0 minus 12 squared is 144 squared divided by 20,000 on the bottom there. And you actually get a value of 0.0072 meters per second squared. Now, this is a dangerous way to do it because one, you are working with a lot more complicated functions like squared and things like that. But the other reason why it's dangerous because you're assuming that the oil tanker will come to a stop. Nowhere in the question does it specify this. All right, but you notice how my answers are pretty much the same down to one digit. Okay, so just be careful about that. I would stick with the easier one, which is F equals m times a, but totally up to you guys. And we come to the last question, which is the airplane. So the diagram shows an aircraft and the horizontal forces acting on it. So you have the horizontal forces on the front and the back. On it as it moves along a runway, the resultant force on the aircraft is 0. I know it doesn't look like it, but that's what the question says. So the resultant force is 0. That's important. The aircraft has a takeoff mass of 32,000 kilograms. Each of the 4 engines can produce a maximum force of 240 kilonewtons each. Calculate the maximum acceleration of the aircraft. Show clearly how you work out your answer and give the units. All right, so there's your other numbers that you need to know, and let's work this out. Okay, so first let's think about what is given to us. So we have our mass, which is 320,000 kilograms, and we have some form of force, which is in kilonewtons, and that's not right because we want our force to be in just newtons. So we're going to switch that. But before we do that, we have to think about we need to figure out the maximum amount of force, right? So there's 4 of them, and each one can produce 240 kilonewtons. So what we want to do is we want to multiply each one by 4, and so the maximum force that we can get from this aircraft is 960 kilonewtons, or 960,000 newtons. Okay, so changing kilonewtons to just newtons, you just multiply it by 1,000. And that gives us the numbers that we need to figure out acceleration. So same thing, we have A equals, wants to be the start of our equation because we're calculating for acceleration. And so we have A equals F divided by M. And you just substitute in the numbers. And then you get A equals 3 meters per second squared. So the 3 points here comes from the substitution, the answer, and the conversion of units from kilonewtons to newtons. So whether you did 240 to 240,000 first and then multiplied by 4 doesn't really matter. As long as you get 960,000 newtons at the end of it, that's all that matters. Okay, and for those of you that are a little bit more curious about why I use 240, because it says each of the 4 engines can produce a maximum force. You might be thinking, well, why didn't you use 200 or 180 or 140, right? And that's because it's asking for the maximum acceleration. So you want to figure out, if I put out the total force that this airplane can produce, how much acceleration am I going to get? And this is why, okay? So well done for getting to the end of that. I know there's a lot of practice problems and you might be thinking to yourself, I got a lot of those wrong and I don't understand this. Go back and re-watch some of the sections because really Newton's first and second laws of motion are probably one of the more confusing ones, more abstract to understand. So just give yourself enough time to re-watch it, redo some of the questions, and figure out where you're getting these numbers from. So here's your knowledge check. Go ahead and pause the video and answer these questions, and I will show you the answers in a little bit here. Well done, and here are your answers for your 10 questions. There you go, and here's your forces for number 8. So if you want to go ahead and pause the video to copy those down, you can go ahead and do that. But well done for getting it through Forces 2 Part 1. Next time I see you guys will be Lesson 6, which is in Forces 2 Part 2. All right, have a wonderful rest of your day.